All right, so up to this point, okay, as we continue to move forward, how how do you determine the valence number? First of all, what is a valence electron? First of all, so how do you know how many electrons boron or aluminum or gallium have as far as valence electrons? So what column is that? You're right. No. Column 3. Because you put the S block together, which can hold 2, with the P block, which can hold 6. So if it's in column 3, we'll just say aluminum. Okay? Aluminum's in column 3. What period is aluminum in? Okay? So, what two predictions can you make as far as aluminum is concerned? Why is the number 3 third energy level and 3 electrons? Okay? So, when we look at this, remember the electron cloud, that's the most likely place where you're going to find these electrons. Okay? Which makes sense, but are they only located in one spot in that energy level? This is a little higher order thinking. We never discussed that. So in this electron cloud, do they just sit still or no? Yeah, they rotate around the nucleus, okay? So either this is where we left off or this is where we begin. This is where we left off with. Okay, so when we look at this, it is the electrons in that outer energy level that determine the chemical properties. And that's no surprise. How we can describe that is as follows, okay? Just like what we said with aluminum, okay? We know how many protons does aluminum have? So when we say look at element 13, we know we're talking about aluminum, right? Because that's the atomic number, which gives you the number of protons. Okay, so from yesterday, if we want to put the number of electrons that will total 13 out here, you just go down your slide. And remember, you correctly said it's in the third column. It's also in the third period. So there's our period, number 3. We fill up 3s2, and then 3p what? 3p1. Remember, it can hold 6. So I'm just going to put an E there because it's easier to see that. So this is where we get that valence number of 3, because that S block was full and then just one column out of the P block. So valence number and then period number tells you the number of energy levels. But you can't make that prediction with D block elements or what other? Or F block elements. So for instance, someone give me an example of a metal out of the D block. Okay? Chromium we heard first. So chromium is element what? Okay? So if we do some predictions, which we can, the better understanding you have of this periodic table, by now, I think some of you can tell me where those last electrons enter. Which energy level do you think? Now, it's just one. Just don't look at that table and shoot out a number right away. Look at your table and tell me you are correct. Why are you right? Right. Remember we said it's n minus 1. So when you look at a D block element, you see that chromium looks like it's in the fourth period. I would agree. But when you put 4 in for N, you subtract 1, that gives you your 3. So to make sense of that, okay, so very quickly, we're going to do this same process where it's going to add up to 24. 1s2, 2s2, 2p6, 3s2, 3p6. Then your slide rule says what? 4s2. And then this is where your 3 came in. It looks like it's in the fourth period, but it's not, because we got to go back to 3D what? That it holds 10, but what column is chromium in? Okay? So that is, remember we said you can't make that prediction. Well, you can, but you got to be careful when you do that, because you got to say n minus 1. So if we add all these numbers together, that gives us 8, that gives us 12, so that's 20. 4 more gives you 24, so that's got to be right. All right. The only way, and this is a little foreshadowing again, the only way that you can determine how many electrons there are would be something like this. You'd have to be told that information. This is an example of what we'll be doing next chapter. That's a little further away. We know that chlorine's got a -1 charge. So -1 times 3 gives you -3. So to add up to 0, chromium would have to have how many positive charges? 3. So look in your box. Does it say chromium can have a +3? Yeah, and that's where that comes from. So you would have to be told what the charge is to see how many electrons come out of there. But again, that's a couple weeks away. This is a kind of a higher order thinking right now. So if we don't quite understand that, don't worry. We're going to hit that probably pretty hard here in a couple weeks, providing Mother Nature wants to cooperate with us. Was anyone else? I was surprised, but yet I'm not, that we had a late start. You might be sitting there thinking, that phrase makes absolutely no sense. Well, one, when you look at surrounding schools, further south you go, I think Chester is maybe, about 7 miles off of Highway 34? So that's probably the furthest south, would you agree? Okay, so ourselves and Chester would be the furthest south, and if you go east, maybe you got to get into Minnesota. I don't know. So when I say I was surprised that we had a late start because of the number of schools that did not do that, but driving in the country, the bus route after school, I thought your pops was going to get a phone call. I called your aunt, though. So, yeah. And it's one of them things. Okay. We've all been there when, okay, who can we pick on in here? Okay. Well, no, you can't pick on me. But see, this can go both ways. I can see this. So let's say, for instance, you're on your way home, and not that you run out of gas. That's not going to happen. But in this case, we say we are. You ran out of gas on the way home. So you have to call Pops at home, and you're sitting there at the phone, and you're waiting for him to call you back. And let's say it's 2 minutes. Does it seem like 2 minutes? No, you're all shaking your head. No, I would agree. But this is where it can kind of go both ways, because you really don't want him to call you back, because maybe when you got stuck with your tractor, I got to call Pops. I don't want to see what he has to say. But it happens. So. But that's what happened on the bus route. I was going by Jerry's Electric up there. I thought, I'm not going to get through there. Would you agree? So by the time I did go all the way around, I probably wasted about 15 minutes, I think. But anyway, to try to keep this long story short, yeah, I called your aunt and said, yeah, you probably aren't going to get through there. But they were working, whoever plows that township with that big track Case IH. It's got a blade that looks like it's about the size of this room. Okay. But, yeah, I was afraid that I was going to have to make that phone call to say, we're stuck with the bus. And then let's say it says 4:15. Well, we'll call you right back. And like I said, it might say 4:17 when they call you back, but it feels like it's like 4:30, which that time seems to go longer and longer and longer. But so that's what I mean by I was kind of surprised, but yet wasn't. But everyone didn't have any problems getting to school. Well, some of you I know live here in town, so that's going to be easy. But some of you that do live out in the country, that bridge over the interstate, that is awful. That's the worst I've seen that blow in with snow. And maybe it's been worse than that before. Okay. Okay. So that was, I noticed that. I thought that, I didn't know that was intentional. So that was their version of a snow fence. Well, that's whatever we can do. All right. Because we don't want anybody to be late for school. No. But sometimes with some of these mornings, that's the last thing we want to do is see some of you possibly stuck when it's 35, wind chill 35 below zero, because bad things can happen, obviously. We don't want to see that. Okay. So again, these valence electrons are in the outer energy level. Okay. So energy levels are numbered from, yes, 1 to 7. These are your periods. We've talked about that before. These are vertically written, periods 1, 2, 3, 4, 5, 6, all the way down to 7. So out of the first two columns, what's an example of an element in period 2? Just in the S block. Lithium's one, and beryllium's the other. Yes, neon would be in the P block, but yes, that is correct. Now, remember, periods are horizontal rows that go this way. It's just that it's numbered vertically, but they're rows that go this way, and then columns are just that. They're vertical, and those are your valence numbers. Don't get so hung up on these electron dot diagrams. We do this next chapter, because in my opinion, there's no need to throw these Bohr models in these configurations and the dot diagrams, okay? And we've illustrated what that means, and I can show you an example of that really quickly here in just a moment. So I asked the last period class, so you got this late start, so is it more sleep, or is it catching up on some of your TV shows? Sleep. Ah, hey, must be, no, I'm just kidding. Yeah, I got up at the regular time anyway, but The Mandalorian. That is a good show. Anybody else? The Mandalorian. Yeah. No. I'm only on episode 5. Is that like a little tiny Yoda, or what is that little thing?
Yeah, it's like the last Yoda ever. Yeah.
Oh.
And now everyone wants to kill it.
Right. I got that part. Yeah. No, it wasn't very apparent at the beginning. It wasn't until like episode 4 and 5 is where what you say makes sense, that everyone's out to get that little thing. And for those of you who don't follow Star Wars, you could probably not care less about what we're talking about. Yeah. It's good stuff, though. Okay. So, now, the reason this is so important, and they were illustrating that as far as, let's say, regular gunpowder, or TNT is a little too complex to look at, but C4 definitely is too complex to look at. But what happens, okay, like in that C4 explosion that we saw on that video, why is there so much energy given off in some of these munitions? When these molecules break, okay, they release energy when what happens though? You're right, but you're a little ahead of yourself. When they split, but then what happens? Yeah, they combine. So oxygen does that a lot. It'll bind or bond with another oxygen. It'll bond with carbon to give you. And any time these molecules or atoms are broke apart and then reassembled, energy is given off. And as you can see, some of that gives off a lot of energy. I know, talking about the Mandalorian's a little distracting. Yeah. Good stuff. Might have to see if I can get CBS All Access. Anyone watch Criminal Minds? I'm kind of getting into that show. That's a good one too. Yeah. Good stuff. Okay. So even if we didn't see any information here, well, it says column 1. So what's an example of an alkali metal? Okay, and which would make sense. We could pop this open. Sometimes it doesn't happen that easily. So, oh my, I got an interstate battery. That must be a basketball fundraiser. That's where I can't remember who I bought them from. Someone, was it a junior, maybe? Well, doesn't matter. But, and that's why they're called lithium-ion batteries, because it has that alkali metal, lithium in it, okay? I was glad someone didn't say hydrogen. But where's hydrogen located, though? Still in column 1. So if we call them alkali metals, why would we put hydrogen in column 1? It has something to do with its electron. There's only one valence electron. So it's going to be in the same column with other elements that only have one valence electron. I can't remember how this goes. We could say this, I can't remember. This class is like my favorite class, kind of like I'm a hydrogen with one electron. If I only had one choice, should this be the best class? What about seniors? Juniors? Sophomores? Okay, so who's the bottom feeders? Really? That's just your opinion. But maybe some opinions become theories, and then theories can become laws, which means it's just accepted. Kind of like what evolution is. It's just a theory. It doesn't necessarily mean it's a law. It's not like gravity. We know that it's the case anywhere you are on Earth. But just think. What we know about evolution, you can survive by being the most fit, or you can survive by, what do you suppose we mean when we're pointing at your noggin? Your intelligence, yes. Then there's probably some of you out there that have it both ways. This is where you nod your head, yes. Very good, very good. Okay. I think we're about ready to wrap this up. We don't have a whole lot left. Okay, yeah. Okay, so alkaline earth metals like beryllium, magnesium, calcium, strontium, barium, and It's either francium or cesium. I can't remember which. Cesium. I'll go with. Oh, dang it. Okay. Barium, then radium. All right. So, again, when we talk about if it's in the same group, it's going to have similar properties. Okay? So, alkaline earth metals, they're all in column 2. So, they're all going to have 2 valence electrons, giving them not identical properties, but fairly similar ones. And this concept on these electrons is going to become more important for those of you, again, who want to take organic chemistry that's offered here. It's how some of these compounds split apart because of their chemical properties. Because certain elements will hold on to their electrons a little tighter than others. And again, that's a higher order of thinking that we're not too concerned with at this level. So as far as specific names, there's really only 4 that have a specific name. Column 1 and 2, alkaline earth metals. Then column 8, which is your noble gases, and then column 7 has a specific name, the halogens. That's right. Okay? So otherwise, columns 3 through 6, you just call them the top element in that family or that group. Boron, carbon, nitrogen, and oxygen. And by that time you get to column 7 and then 8. Okay? Then we'll wrap it up with talking about the halogens here. Okay? Again, elements in group 7 all have 7 valence electrons. And then finally, your noble gases, very stable, that really don't want to react with anybody. So we could say, is any... It sounds to me like you're a noble gas. The reason why would we say it? No one wants to be around Logan. He's a noble gas. So that's, in a way, that's kind of being mean. You could say that because what's true about column 8 here with these noble gases? Do they react very easily? Some of them don't react at all. They're just too stable, and it takes way too much energy. Now, if you know anything about tungsten inert gases, better known as TIG welding. You ever heard that before? Or wire welding. Some of you farmers may even have a wire welder. So, has anyone ever done that before? Welded. Because you have arc welding and you have this tungsten or TIG welding or wire welding. What happens is, in this case, you have this wire feed that combines with electricity and in inert gas, argon, because I think there's one in the shop. If you go and look at one of the gas cylinders, it's going to say argon on there. Okay? So with that, it's not reacting with other elements, but you need that heat given off. Okay? Because that's what happens with arc welding. You're sending so much electricity through it, it melts the 2 metals together, and then when it cools, then you weld the 2 together. Okay? Now in this case, why not use something like oxygen? Well, for one, it's not that it's unstable, but we really don't want to be sending so much electricity through there you blow yourself up. Because that's probably what could happen. Now you might be thinking to yourself, well, what happens when you're using a cutting torch or oxygen acetylene torch? Well, there you're regulating how much oxygen you're putting through there. So then you have that little thumb. Has anyone ever used a cutting torch? Yeah, you have that little, you press that, and then that sends the oxygen through. Yeah. So, good stuff, we hope. Anyway, does everyone have this information that wants it? Okay. So there's a couple things I want to go over on the board, and then that will be it for today. I see the rest of the week we'll have something for you to work on that I see will be due a week from yesterday or Tuesday. Okay? And I would venture to think that on Monday and Tuesday, we'll see if we need both days for reviewing, and we'll have a two-part exam next week. All right. So a couple of things we want to go over. Won't take very long. As you remember, we're talking about some of these elements that have these similar properties. So, and we've done an example of this before. You just never really knew what it was applying to. So we'll do two examples of each one. Okay, so what do we notice about numbers and letters here? Add them up. Okay, so this is element 19, which makes it what? Potassium. All right, so what about this one then? Numbers and letters. Okay, so 12 makes it element what? Okay, then this one pretty simple. And then this one, did I do the same thing twice? I did. That's not what I meant to do. Okay. I think the simplest way to fix that would be do a 2 and a 6, and then, there we go. Okay, so 20 makes that what then? Okay, so why is it that this magnesium and calcium, they're not going to have identical properties, but they're going to have really, really similar ones? True, they're both alkaline earth metals, but more importantly, that's okay. Now you're right, but you're getting way ahead of yourself. Has something to do with the letter V, valence electrons. Okay, so how many does calcium have? In the outer energy level, 2 valence electrons. Same thing with magnesium. They both have 2 valence electrons. So they're going to have very similar properties. And like what you yourself had said, if these get donated, okay, it's like maybe if you went to the movies last weekend, guys, you reach in your wallet and pull out them $5 bills and make it rain. Something like that, maybe, yes. So then, once these electrons had left, they're no longer there. We still have 12 positive charges. How many negative charges do we have? And we add them two numbers together, it gives you +2, and that's why you look inside your element box. Magnesium has a +2 charge. Okay? So, on the other end, if we were to do something like this, okay, again, this is a little bit of a foreshadowing on what we're doing. If we put the number 5 here, we're changing that from calcium to what instead? Okay, so when you look at this, the outer valence, there's 7 valence electrons. Okay, so that must mean it's which type of element on that table. And this, what are they called though in the 7? They're called halogens. Okay, so this is now chlorine, okay? So to become stable, and that's what that video had alluded to, they're saying it's kind of like a shell game. When they're playing that, what these elements want to do is have an outer energy level that's full. And chlorine is how many short? 1. Because remember, these all go by the digit 8. That's what we refer to as an octet rule. So when it was talking about those electron dot diagrams, where it said what dots and X's represent valence electrons, do you remember writing that information down? Yes? Okay. So if we see chlorine, if we're going to make X's around there, you don't have to write this down. We'll be going over this again in a short amount of time, but these 7 X's are representing these 7 valence electrons. So to become more stable, it wants one more, and that's where that hydrogen's going to go. It's going to give that electron to there. Okay, so now this electron is over here, and now we've created a chemical bond. Okay, and this is now stable with chlorine. I didn't do this intentionally. Sometimes that's how it works out. I guess you could say this is kind of funny. Hee hee. That's a real knee slapper, isn't it? We'll leave it at that. I see a lot of, I'm not saying blank stares out there, but gee, makes it sound like we were talking about the Mandalorian or something. Yeah. All right, I digress. Okay, so that's it for today. We'll have that assignment for you to work on tomorrow, and then we'll start reviewing for this chapter, and then get to those dot diagrams probably sometime later next week. Okay, catch up to you next time.